Hello everyone, this is our presentation of the final power electronics project for the electrical engineering course at the Federal University of Santa Catarina. My name is Lorenzo Borges, and together with my colleagues Luiz Felipe Flegger, Matheus Lenzi, and Jorge Liberato, we are going to present the high-frequency switching converter, the project that we developed. We received the following voltage and power specifications, and we choose the DC-DC boost converter configuration because the output voltage range is greater than the input voltage range by a maximum factor of 3. So it was not necessary to opt for a flyback converter, which would be an unnecessary high costly option. Same with the buck boost converter as long the only demand is to elevate the voltage. Starting with this choice of commercial semiconductors, we will explain the theoretical specifications obtained from the ideal components for choosing switches and diodes. And for the diode, we first calculated the maximum reverse voltage and the maximum current, and we made it a prerequisite. Likewise, the Schottky diode was used, as it will have a low voltage and a large current, a range of 50 amperes. For the choice of key, we calculated the maximum average currents, the maximum voltage, and we made it a prerequisite. We reached the option of two switches, MOSFET and IGBT. For the sake of opting also for a high switching speed, which is beneficial for choosing better capacitors and inductors, we've opted for MOSFETs. And for on the configuration of the boost converter architecture, we know that the maximum voltage across the switch is equal to the maximum output voltage. Thus, according to our output specifications, with a maximum voltage equal to 15 volts and considering a safety margin, we decided to choose the MOSFETs with drain source voltage equal to 40 volts. So we made a spreadsheet containing three different options for each component, and it's possible to access the datasheet of each element and as well the technical and price information. The inductors and capacitors have been designed in such a way that they can withstand the large currents that may have in the converter and that allow a low ripple of current and voltage. The project was made to operate in continuous condition mode. However, for very low loads due to the limitations of the components, it operates in discontinuous mode. Now, we provide the theoretical and the simulated yield curve for each type of operation. The heatsink was also projected in the condition where there are greater losses in the switch and in the diode. For instance, the input and the output voltage are the lowest possible, 5 and 12 volts, because the current will be greater and consequently there will be more losses. It is designed to maintain the temperature at least 10 degrees below the maximum junction. So let's simulate.
This is our schematics on Typhoon Hill. First, we have the voltage source. This is the inductor and the inductor load. We have also measurement devices here. We placed the capacitor and its resistance, as well as an ammeter to measure the current, so it's possible to calculate the loss. Here we have the load being variable and controlled by the scaler, and this is the boost converter, which we can control the commutation frequency here, as well the parameters of the losses, which can be controlled by the current or the voltage or the temperature as well, as you can see here. And this is the reason that we got the temperature inputs on the scaler. To finish the plot, there is the duty cycle and the enable to control the boost converter. So here we have a simulation on the scaler. Basically, we can adjust the input voltage and see its output. Here is the duty cycle controller, enable switch, load controller, and the temperature control on the switch and the diode. In the diodes, we have the output voltage, the output current, output power, input power, the efficiency of the system, the losses of the system as well. And here we have the waveforms. Firstly, the current on the inductor, output current, And finally, the voltage waveform.
So thank you for your attention, and here are the contacts of the members of our group.